All right, welcome everyone to today's video. So we're going to be starting talking about spectroscopy. Okay? So spectroscopy is something that will probably be most relevant to most of the work that you may or may not be doing in a chemistry lab, right? So we often deal with spectroscopy all the time when we try to probe and analyze what's going on in our systems, right? In solutions and materials, gas phase experiments, whatever the case may be. Often we're probing things using spectroscopic techniques, okay? Because that's typically the best way that we have to try to probe and analyze and determine what is happening with what we're interested in. So as just kind of a review here from previous lectures, just to kind of keep us reminded of energy levels and things of that nature as we start talking about them related to spectroscopy, right? We want to consider the following set of orbitals, right? And the question is which one is an actual orbital that can exist, as in obeys the set of rules for the quantum numbers, and has the highest energy amongst those orbitals that can in fact exist. Okay? And so, right, if we were just asking which of these orbitals would have the highest energy, right, the answers would be these like 5 orbitals, okay? Because those will have the highest energy because their principal quantum number n equals 5. But with principal quantum number n equals 5, the highest quantum number for L equals 4, okay? Which that is, L equals 4 is a G orbital, okay? And so these 3 orbitals here, 4G, 5H, and 5I, do not exist, okay? Neither does the 3F orbital, that is not a valid orbital. And so 4F here is the highest energy orbital that does in fact exist. All right. And delete this slide. Okay, so spectroscopy, right? Spectroscopy has to deal with light interaction with matter. Okay? And so we will often talk about absorption spectroscopy, but there's also emission and stimulated emission, and we'll talk more about those things, right? So, right, so absorption in spectroscopy is when you hit an object with light or a photon, okay? That photon, the energy of that light or that photon is potentially absorbed by the molecule, right? And that induces a change in state, okay? Right? If we're talking about absorption, the energy will be absorbed, right? And when it's absorbed, it changes the state of the molecule, whether it be its vibrational state, rotational state, electronic state, right? All these different energy levels that we've been talking about, right, can be modified through the absorption of light, okay? That's how we transition from one state to another, right? You can think of this as sort of, right, if you're playing pool, right, one billiard ball hits another billiard ball, and, right, in that collision, it transfers all of its kinetic energy to the other ball, and that ball starts moving, right, and it goes from having no kinetic energy staying still to having some amount of kinetic energy, right, that has gained from the other ball, right? And so you can imagine that light is, you know, the cue ball comes and hits one of the other billiard balls. Let's say you know, it stops from that collision, right? And all that kinetic energy then gets transferred to the other ball, okay? And light, sort of, this classical physics and things like that, absorption of light and emission of light during these events, energy must be conserved as well as momentum and angular momentum. Those things must be conserved, okay? So you have the total energy, total momentum, total angular momentum, all those things must be the same before and after an absorption event occurs, okay? And from that conservation of energy, when light is absorbed, right, the light goes away and all of its energy has to go somewhere, and that energy goes into the molecule by changing its electronic vibrational rotational state. Okay, Emission is the same type of process as absorption, but instead of going from a lower energy state to a higher energy state through the absorption of the energy from light, right, you go from a higher energy state down to a lower energy state by emitting light. Okay, so now your molecule has decreased in its energy, and that decrease in its energy means that it's got, you know, that extra energy has to go somewhere, and it goes somewhere through the emission of light. Okay. And again, when we're talking about light here, we're not necessarily talking about visible light, right? Infrared, microwave, right? There's a whole spectrum of light in terms of its energy, and it's not always visible. Okay. And so one of the key equations to keep in mind whenever we're talking about spectroscopy is this simple looking equation here, that the change in energy that occurs in your molecule, right? So this occurs in molecule, right? So this change in energy that occurs in your molecule, right, corresponds to the energy of light. Okay? Right? And the energy of light can be reported in terms of frequency, wave numbers, wavelength, electron volts, whatever the case may be, right? Right. This equation here is essentially, again, saying that change in energy for your system, right, for your molecule, is related to the energy of the photon, right? And the energy of the photon is h times nu. Okay? Right? And so, right, that's very, very key, because whenever we're, say, plotting some type of spectra, right, if you have some type of absorption spectra, right, often think of just microabsorption, absorbing, emitting of visible light, right, you'll have on your x-axis will be the energy of your photon, right, expressed in terms of wavelengths, right, inverse centimeters, things like that, right, and you'll have peaks that appear, right, in this spectra, right. Well, where these peaks appear at the energy of the photon, right, that is the energy difference between whatever initial and final state your system transitioned to, right. This is meaning that, right, this energy difference between your initial and final state, right, is related to the energy of that light, right. So peaks in your spectra, where those peaks are, is telling you the energy gaps in your system. What are the energy gaps between different states in your system, right? We talked about in quantum mechanics, right? Everything has discrete energy levels, right? So there's different energy gaps, and the energy gap, right, between different energy levels is what we're probing in spectroscopy. Okay. Right. And so here, looking at right, absorption and emission spectroscopy, there's another type of spectroscopy called Raman spectroscopy. So Raman spectroscopy is not so like absorption and emission, right? So infrared, say, absorption is shown kind of here, right? You just absorb a photon, right? You have a photon initially, then you don't have a photon that exists, right? For Raman spectroscopy, this has to deal with the scattering of light. So what will happen is light will come in to your molecule, it will hit the molecule, and then you can think of it as sort of bouncing off, but when it bounces off, it either takes in some amount of energy or gives off, or gives some amount of energy to your molecule through that scattering event, okay? Right, so you can think of with your billiard balls, right, instead of the cue ball coming, hitting one of the other balls and coming to complete stop, instead it comes, hits the other ball and bounces off, and it has a reduced kinetic energy, but it still transferred some kinetic energy to the other billiard ball, right? And so that's what's happening, okay? So pure Rayleigh scattering is no induced transition. It's just literally the light scatters off your molecule, its frequency, its energy stays the same. Nothing really exciting happens here, right? And then there's what's called Stokes Raman scattering, okay? So Stokes scattering here, right? That Stokes scattering is when the energy of your light has decreased slightly and you've caused a transition in your molecule where it goes from a lower energy to a higher energy state, okay? And then anti-Stokes scattering, right, that is when your molecule goes from a higher energy state to a lower energy state and gives off some of its energy during the scattering process from light. Okay. So again, Stokes scattering, your molecule absorbs some amount of energy. Anti-Stokes, your molecule emits some amount of energy. So the main difference between Stokes and anti-Stokes, Raman scattering or Raman spectroscopy, right, compared to absorption and emission spectroscopy, is purely that you have a photon before and after this kind of absorption or emission event, right? In Raman spectroscopy, this photon is existing before and after, right? It's just its energy has changed due to the interaction with this molecule. Okay. Right. And so talking about kind of absorption and emission energies for different transitions, right? So things like microwave light, okay, very low energy light here. I'm giving all the energy of the light in electron volts, right? This is related with rotational spectra, or kind of on the microwave side of things, right? Right, that's how your microwave works, is using microwave radiation to rotate the water molecules in your dish that you're microwaving, right? And then that heats up the system by adding kinetic energy to those water molecules by increasing the rotation, right? Increased kinetic energy is increasing its temperature, and that's what heats your system, or your food, right, in a microwave. Okay. Infrared spectroscopy, IR spectroscopy, that's vibrational spectra, right? IR spectra, right? You hear that all the time, thinking vibrational spectra, IR spectra are related with each other, right? And that's, again, your IR spectra are probing vibrational modes. UV vis, right? Ultraviolet to visible light is electronic state transitions, okay? And those are typically your HOMO to LUMO type excitations and things like that, low energy electronic transitions. And then when you get to high ultraviolet light, you can either be ionizing some systems, so you could, right, the photoelectric effect uses high ultraviolet radiation to remove an electron from a system, right, or you might be causing an excitation from a core electron to some valence excited state, okay? And this ultraviolet radiation is often used for X-ray spectra and things like that to determine crystal structure, as well as to then probe and analyze what different types of metals and materials are in some type of solid that you may have. Okay, so what determines whether or not something is absorbed or emitted? Okay. That rate of absorption and emission and whether or not it occurs is given by this formula here. This is referred to as Fermi's golden rule. Okay, this Fermi's golden rule. Okay, the key things to note here, right, is right the rate in which you are absorbing, how fast are you absorbing, depends, right, on the number of photons you're hitting it. The more photons hit your surface for some period of time, the more absorption events you're going to have, right? Because each absorption event has some probability of occurring, right? And so the more photons you have hitting your surface, the more absorptions you're going to have, which is related with the intensity of that light. Okay? Omega here is the frequency of light that's used, the energy of that light. Okay, C, it happens to be the speed of light, which is constant, right? And the key thing out of this that we'll focus on in this class at least is the transition dipole moment. Okay, so mu IF here is called the transition dipole moment. It has to do with the interaction between your initial and final states. Okay. And this interaction between your initial and final states is key. If they don't interact, then this transition dipole moment is zero, and there is no transition between those states, and thus you will have no absorption or emission event occur at that given energy level, or the energy separation between those two states. Okay. So what is this transition dipole moment? So mathematically, right, this is just a simplified way of writing this integral here. Right, I could put like d tau, right, integrating over all space, okay, of this dipole moment operator in between your initial and final wave function, okay, right? Classically, what this is basically trying to say is that a dipole moment has to exist between your initial and final state, right? Or a change in dipole moment for that light to interact with it, right? And the reason is light is an oscillating electromagnetic field, right? So light is this oscillating electric field, right? Right. This is your like electric field here, right? For light, it's an oscillating electric field, right? For that to interact with your molecule has to have some type of a dipole moment, okay, where it has a negative charge, right? Let's pretend it's a very simple dipole, right? It has to be this type of dipole moment that exists from this electronic transition, right? Because then this dipole can interact with this oscillating electric field and absorb the energy of that field through then moving the dipole moment. Okay, so this can be all related back to classical mechanics, where if you have if you have an oscillating electric field, right, and you have a dipole, that dipole will eventually start oscillating with that electric field and then absorb the energy. Okay, think of this as someone's screaming, right, or singing at extremely high pitches and potentially breaking a glass, right? What's happening there is that high-pitched singing or screaming or whatever, right, is occurring, and it's creating, right, this oscillation, these sound waves, which is these oscillating waves, right? These oscillating waves hit the glass, and if they oscillate at the right frequency with that glass, then that glass is able to absorb that oscillation and keep on absorbing and absorbing and absorbing that oscillation until eventually the glass is vibrating so violently that it shatters and breaks. Okay, so that's what's happening in spectra, right? When you're probing something with light, this light is this oscillating electric field, right? That oscillating electric field interacts with your molecule through this transition dipole, and if this transition dipole matches up with this oscillation of this electric field, then it can absorb that light. Okay, so the stronger your transition dipole, the more it can absorb light and the more readily it can absorb. Okay, so right, note here then, if your transition dipole is 0, okay, that means you cannot have any transition occur from that initial to final state. Okay, which means that there will be no peak that appears on your spectra related to transitioning from some initial and final state when its transition dipole is 0. Okay, right, and so we'll go over these selection rules over the next series of lectures, right? But there's a number of selection rules based off of the transition dipole moment of when it's not going to equal 0. Those are given here, right? In terms of atomic spectra, rotational Raman, and vibrational spectra, there's different selection rules for the changes in the quantum numbers related with those energies, right, that must occur through the absorption or emission of light. All right, so just do a quick clicker question here, right? So it's a multiple choice question, right? The intensity of light, right, the intensity of an absorption line is typically determined by what? The wavelength of that transition, the value of the transition moment interval, right? Only the lifetime of the final state, or only the population of the final state, right? As we're talking about, it has to do with B here, the transition moment, transition dipole moment, often is what I'll refer to it as well, right? But that's the same type of thing. Transition moment, transition dipole moment, referring to the same thing, right? That is determining the intensity of that peak. And finally, last kind of quicker question related to spectroscopy. A transition that represents only changes in rotational energy appears in which spectral range? Microwave, infrared, visible, or X-ray, right? We talked about earlier, it is microwave radiation, okay? Right, infrared is for vibrational spectra, right? Visible is electronic, and X-ray is either ionization of molecules or completely removing an electron, or core excitations and things of that nature. So that will be it for just our general introduction to spectroscopy. We'll next spend a lot of time on a number of future lectures talking about different types of spectroscopy in more detail.